Okay, so this is the walkthrough for the 2023 higher paper. I'm afraid we're back to the flickery screen and the small paper, but I'm sure we'll cope. So question number 1. So as you can see, question number 1 is taken from the organic chemistry or the crude oil section of the syllabus. And it tells us that the molecular formula of 5 carbon compounds A, B, C, D, and E are shown below. So if we look at these, we might recognize C3H6. So that would come from the general formula CnH2n, which makes it an alkene. This has got the OH group on, which comes from the alcohols. You might remember that from the fuel experiment that you did. C4H8, again, that fits CnH2n. That's an alkene. And then the final two, they would fit the general formula CnH2n plus 2, making them alkanes. Okay, so alkanes are compounds with the general formula CnH2n plus 2. Give the letters of the two compounds that are alkanes. So we've already identified those as D and E. Give the name for compound A. So for compound A, it might be an idea just to draw it out. Although it does ask us to draw compound E down here, so we'll perhaps do it out there. So it's got 3 carbon atoms in it. We know from the general formula it's going to be an alkene, which means it's got a double bond, and it doesn't matter which of those two you put the double bond on. And then consequently, we can add in the extra hydrogens, okay, which would fit on each of those bonds. So it's got 3 carbons in a row, it's got a double bond, so it's propene. The prop coming from the 3 carbons, and the ene coming from the double bond. Okay. Draw the structural formula of compound E. So compound E is going to be not dissimilar to that one, but with an important addition. It's going to have 3 carbons in a row. And then as it's an alkane, as we've identified previously, we can place all the bonds on the carbons, making sure that every carbon has 4 bonds. And we can add in the hydrogens just for make sure we've done the full job. Okay, and that gives us propane. So it's 3 carbons, no double bonds. So that would be propane, although it doesn't actually ask for the name there. Okay, so moving on to this question. This question combines the test for alkenes plus polymerization of alkenes. So the following diagram shows 2 reactions of ethene. So this here is the ethene because it's got 2 carbons and a double bond. The test for ethene, or test for any alkene, is the addition of bromine water. Okay, we're going to fill in the structural formula of the product just here. But also we've got the catalysis, the polymerization by catalysis of ethene to make a polymer. Okay, and we can recognize that from these big brackets with the bond going through the brackets to show that this is a repeating unit. Okay, so complete the structural formula for molecule X and repeating unit Y. So if you add bromine to ethene, what you're doing is you're adding a bromine atom to either each of the 2 carbons, because the bond opens up, the double bond opens up, and bromine is attached to either side. So to some extent it doesn't really matter what order you put them in, but you do it like that. Makes it clear that the bromines are being added to each carbon. So it's a similar structure to this, except we open the bond up and we add bromine to each side, and it's already balanced because the bromine atoms, the bromine molecule rather, splits up to form 2 bromine atoms that are attached on both sides. Okay, and then the repeating unit for this, okay, is relatively straightforward. We remember that the double bond opens up, so that just forms a single bond between the 2 carbons, but we've still got the 2 hydrogens on each carbon. So that is the repeating unit. So that's the repeating unit for polythene. So describe the change that would be seen in the orange bromine water when molecule X is formed. And the best word to use there is the bromine water decolorizes. So when the brown bromine water becomes part of the 1,2-dibromo ethane, basically the color of the bromine disappears. Name the type of reaction that's taking place to form repeating unit Y. Well, that would be polymerization. Whilst it's the only type of polymerization at GCSE, its full name, oh sorry, I realised that's not on shot. Its full name would be addition polymerization, because you're simply adding molecules together. Okay, so addition polymerization. Okay. The addition, I think, is actually optional. Okay, moving along. Paper and plastic are both used to make disposable shopping bags. The table compares the percentage of disposable bags, paper and plastic bags used by consumers in a Welsh town between 1988 and 2018. Okay, so if we look across, the amount of paper bags started relatively high. It decreased, but then it started to increase again after 2013. And basically the opposite pattern happens with the plastic. They increase, and then they start to decrease again. Okay, so in 2003, the consumers of the town used a total of 1.25 million disposable bags. Use the information in the table to calculate the number of bags used. Okay, so if we take 1.25 million and we multiply it by the percentage of paper bags, and that will give us how many actual paper bags were used, okay, because the disposable bags include both types of bag. Perhaps the quickest way of doing that for 2003, I'm looking for paper bags, is to multiply that by 0.12, because 0.12 is 12% expressed as a decimal, and that will just give us the answer directly. So 1.25, we don't need to worry about adding the millions in, times 0.12, and that gives us 0.15 million. Okay, so 0.15 million. So if we just use the calculator as it's here, it gives us 150,000. Okay, so no, actually it wants the answer in million, so actually we can leave it at 0.15. 0.15 million. Okay. Okay, so the next part of the question is the inevitable graph question. Slightly unusual graph in this instance, though. So the graph below shows the percentage of paper bags used between 1988 and 2018. Plot on the same grid the percentage of plastic bags. Sorry, paper bags. This is the paper bag plot, and it wants us to plot the plastic bag plot. So you can probably imagine that it's going to be a mirror image of this graph here. So let's have a look. So we start off with in 1988 with 27%. So there's 20, and then 27 is there. Then it's 37 in 1993. So that's just there. Then it's 69 in 98. So 69 is there. Then it's 88 in 2003. So 88 is there. And then it's 92 in 2008. So 92 is there. Then we're down to 87 in 2013. But 87 is there. And then we're down to 79 in 2018. So 79 is there. And we need to join those up as carefully as we can. Okay, so there's our plot, and we get the 3 marks for accurate plotting and a suitable line. Okay, so unfortunately this is going to involve a bit of turning back and forth. So the next question says, use the graph to answer the following questions. So give the year when equal numbers of plastic bags and paper bags were used. So if we refer back to our graph, if we wanted to do it properly, we can find the point at which the 2 lines intersect, and then we can drop down a vertical line. It might be slightly easier if this was a full size copy of the paper. Okay, so 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 it's 93, 94, 96. So 1996 is the year of parity between paper and plastic. Okay, so 1996. And then the next question says, circle the simplest ratio that compares the use of paper bags to plastic bags in 2000. Okay, so paper to plastic, so the year 2000, so 98, 99, 2000, so it should stay on the line. So we've got there 20%, if there's 20% of one, there is therefore 80% of the other. My line doesn't quite reach that, but that's due to my drawing not to, it has to be 80% because it's a percentage, of course. Okay, so that's 20, so basically that's 1 to 4. Okay, so that one is that one there. Okay, so it's a 1 to 4 ratio because 20 to 80 is the same as 1 to 4. And then give one reason that explains the change seen in plastic bag usage in Wales between 2008 and 2018. Okay, so this is sort of a knowledge question. There's various reasons here. There is a greater awareness of the problems with plastic bags. There is the initially there was a voluntary charge by shops on plastic bags, and that became a mandatory charge. The government introduced a mandatory charge of 5p on every plastic bag, and then of course there was the existence of bags for life, okay, which became or have become possibly rightly quite popular, so that you can reuse your bags rather than taking the bags home and throwing them out, which definitely used to happen back in the 80s. Okay, moving on to question number 2. Okay, so question number 2 is from the structure and bonding aspect of the course. So the table gives the electronic structures of sodium and oxygen. Okay, so we've got the 281 and the 26. Sodium reacts with oxygen to give sodium oxide. The diagram below can be used to show the electronic changes that occur as sodium oxide is formed. So to be fair, they've done quite a lot of the work for you. Complete the drawings by drawing arrows to show the movement of electrons between sodium and oxygen atoms and giving the charges of the sodium and oxide ions that are formed. Okay, so basically sodium has got 1 electron in its outer shell. To get a full outer shell, which is what bonding is all about, it can lose that single electron. So this single electron here can be lost to that oxygen. And then this single electron here could also be lost to that oxygen because oxygen has got 6 electrons in its outer shell. It would like 8, so in gaining those 2, it gains 8 electrons. However, in doing that, it becomes negatively charged twice, okay, because it's got 2 extra electrons, if you like. But in losing those electrons, then these 2 ions become positive. You could put the 1 in, but it's not usually necessary. So that will suffice. And then moving across the page now, draw dot and cross diagrams to show the bonding in an oxygen molecule. Now oxygen obviously consists of non-metal, okay, so it's a different type of diagram. It's not a diagram showing the loss and gain of electrons. It's a diagram showing electrons being shared. Now oxygen, as we've seen from the previous question, has a configuration of 2,6, and consequently it wants 80 electrons in its outer shell. So to get that with only 1 other atom, it has to share 2 pairs. So I'm going to put dot across, dot across. So these crosses belong to this atom here, and this atom should have 6 electrons in its outer shell. So it's now got the 6 crosses, 2 of which are shared, and these 2 dots, I'll make that one a bit clearer, and that one a bit clearer. These 2 dots belong to this atom, so we need to draw another 4 because the configuration is 2,6. We haven't drawn the inner shells because they're not necessary and simply overcomplicate the diagram. So that structure represents the fact that oxygen has a double bond, okay, because it's got two pairs of electrons, two shared pairs. Okay, moving on now. Diamond and graphite are both made from carbon atoms. Their structures are shown below. So we can see in the diamond that each atom is bonded with a full covalent bond to its neighbours, and if we take one that's sort of in the middle of the structure like here, we can see that each atom has got 4 bonds going to other carbon atoms, and consequently that means that all the electrons on the outer shell of a carbon atom are involved in bonding. However, in graphite we can see that each atom is only bonded to 3 other carbon atoms, and consequently it has the capacity to produce these delocalized electrons. Okay, so these dotted lines represent delocalized electrons. So with that in mind, we'll have a look at the question. It says, state which structure is able to conduct electricity, give a reason for your answer. So the answer is graphite, and it's because it has delocalized electrons. It has layers of delocalized electrons. That can carry charge, just squeeze in. Okay, state which structure is used as a lubricant, give a reason for your answer. Okay, again, graphite. Okay, and it's graphite because the layers, the carbon atom layers, are loosely bonded by the delocalized electrons. So this layer here can slide that way easily compared to this layer here, and consequently this material can be used as a lubricant for fine machinery. Okay, so it's oil, where oil's too sort of sticky, if you like. Graphite can be used in things like clockwork watches. Right, give the name for another form of carbon that is used in drug delivery systems. Okay, so that is one of the newer forms of carbon, the newer allotropes of carbon that have been discovered in recent years. So it could be buckyballs, or their larger cousins, nanotubes. To the best of my knowledge, this is still a very, very new technology, and I'm not sure that it's actually been released into the general public as yet. I could be wrong. Okay, this next question. Bond energies. Looks rather daunting, but hopefully we can break it down. So propane gas, which we met earlier in the paper, is commonly used as a fuel. Okay, so it's the fuel used in red gas cylinders you might find on a caravan park. The burning of propane gas is represented by the following equation. So here we have the full displayed formula for propane with all the bonds present. Here we have a large number of oxygen molecules, similar to the ones we saw in the previous question. These are carbon dioxide, you can see the C and the two O's, and these are water molecules, and all the bonds are displayed for you to be able to work the energy required to break or make the bonds. So the relative amounts of energy needed to break some of the bonds are given in the table. Okay, so you'll notice it's only the carbon and the carbon hydrogen and the carbon carbon bonds. So the only information we're given is how to break up this molecule here. So let's see what the question says. The total energy needed to break all the bonds in the reactants. Okay, so the reactants are these molecules here. Calculate the energy needed to break one oxygen double bond. Okay, so what we need to do is to calculate the amount of energy required to break up a propane molecule, and we can take that away from this value here, and that will give us the energy required to break up the 5 oxygen bonds, and if we then divide that value by 5, we'll get the energy required to break one oxygen double bond. Okay, so our first calculation is going to be 6. No, sorry, our first calculation we need to work out the energy required to break up the propane, don't we? So let's do that first. So the carbon-carbon bonds in this molecule, there's 1, 2 of them. So it's 2 times 348. Okay, 2 times 348. I shall use this to ensure I make no foolish mistakes. So that's a 5. A foolish mistake using a calculator. Right, 2 times 348. 696. And then if we count the carbon-hydrogen bonds, there are 1, 2, 3, 4, 5, 6, 7, 8 of them. Not surprising because there are 8 hydrogens. So that's 8 times 413. And 8 times 413 is 3304. If we add those two values together to get the total amount of energy required to break up the propane, it gives us exactly 4,000 joules, which is interesting. Kilojoules, actually kilojoules, 4,000 kilojoules. Okay, so if we take that value away from this value, we'll get the amount of energy required to break up all of the oxygen molecules. Okay, so if we go with, where's the plus minus? So if we then add that to 6490, 6490 gives us 2,490. So 6490 take away 4,000 is 2490. But that's the energy required to break up 5 oxygen bonds. So we need to divide that value by 5. Okay, so it's 5 because there are 5 bonds here. So if you divide that by 5, it gives us 498. Okay, so that's the energy required there. And all these values, we can consider them to be positive because it's energy going into the sister in order to break bonds. Okay, so those are all positive values. Okay, the energy released when all the bonds in the product are formed is 8542. Take the correct overall energy change for this reaction. Now this value here is considered to be negative because this is lost from the molecules and released into the surroundings. Okay, so it's the energy that we can measure as an increase in temperature. So to calculate the overall energy released, because of course the energy required to break the bonds is taken out of that, we can do the calculation 6490 because that was the value, the total value. Take away the energy released 8542. Okay, so if we do that calculation, 6490 take away 8542 gives us minus 2052 given out. So it's given out from the molecules into the surroundings. Okay, so it's that one there. Okay, so that was the question on energetics, or a question on energetics. So moving on, this page is moving. Come on. Okay, more propane. Okay, so propane gas is commonly used in camping stoves. Oh look, a red container. The photograph shows a camping stove being used to heat 750 grams of water. When heated for 10 minutes, 220 kilojoules of energy was transferred to the water. Use the following equation to calculate the temperature rise of the water. Okay, so I need to use the values given in the question and plug them into this equation here. So the temperature rise, so delta T, which is the way we represent temperature rise, is the energy transferred. Okay, so that value there, so it's 220 kilojoules divided by 4.2, and 4.2 is known as the specific heat capacity of water, but as far as we're concerned, it's a magic number. and the mass of water, so we're told it's 750 grams. Now, there's a little subtlety we need to bear in mind. This calculation is based on joules, and our value given to us in the question is in kilojoules. So we need to convert that into kilojoules by multiplying it by 1,000, because a kilo means 1,000. So that's 220,000 kilojoules rather. And we'll just double check that there's nothing funny going on with the mass. So it's mass of water in grams, and we're given the mass of water in grams, so that's okay. So if we divide 220 and then 000 by 750, we get 293.3 recurring. Okay, so oh sorry, I forgot a key step. I was thinking that's a very high temperature increase. I forgot the 4.2. Okay, so let's try that again. Let's do it right this time. So 220,000 divided by, and we'll put it in brackets just to be safe, 4.2 times 750 gives us 69.84. Okay, and the question doesn't demand that we quote it to a certain accuracy, so we'll quote it to one decimal place. That's 69.8, which is somewhat more sensible, because that's the sort of temperature rise we'd expect when we're heating water from about 20 degrees Celsius. Okay, the energy profile diagram for the combustion of propane is given below. So here this is the propane and the oxygen, and this is the carbon dioxide and the water we saw in the previous part of the question. Draw an arrow on the diagram to show the activation energy. Label this A. So the activation energy is the amount of energy you've got to put into the system to get it going. Okay, so that's the difference between the energy of the reactants and this peak. Okay, so we could, and we need to label that A, so it needs to be very clear. And then draw an arrow on the diagram to show the overall energy change. Okay, so the overall energy change is the equivalent value to this here. So it's the difference between the energy required to break all the bonds and the energy released when all the bonds are made. So actually, that's the difference, that's the energy change between the reactants and the products, and that wants to be labelled B. Okay, so that's the energy released into the surroundings. Okay, number 4 looks like a blast furnace. So iron is extracted from iron oxide inside the blast furnace. Iron oxide, coke and limestone are all fed into the top of the furnace. Describe the two main functions of the coke in the furnace. So coke is pure carbon, so it's burnt in the furnace in air, and that produces a lot of heat. So coke is a fuel to create heat, and heat is needed for the many reactions that go on inside the blast furnace. But it's also there because it takes part chemically in the reduction of the iron oxide, the production of iron. Okay, so coke forms carbon monoxide, which reduces, make it clear, the iron oxide. And that's actually the key to the blast furnace. That's what a blast furnace is there for, is to reduce iron oxide to iron. Okay, to iron. That's why we have blast furnaces. So those are the two roles that coke performs inside the blast furnace. Okay, limestone is added to the furnace to remove some of the impurities as slag. The removal involves a two-stage process as shown in the following equations. So the calcium carbonate is heated because there's a lot of the coke is burning, and it decomposes to form calcium oxide and carbon dioxide. And then the calcium oxide reacts with the silicon dioxide, which is the sand, which is the impurity in the hematite, in the iron ore, and that produces slag, which significantly we're not given the formula for. So a group of students were each asked to calculate the maximum mass of calcium oxide that could be produced from 8 grams of calcium carbonate in stage 1. the answers they calculated were as follows. Okay, so basically we need to find out which one of these people is correct. So we're told in the question that we're starting with 8 grams of calcium carbonate. We can also see from the information in the question that every 1 mole of calcium carbonate makes 1 mole of calcium oxide. So if we know how much calcium carbonate there is, we can then use the masses down here to work out the mass of calcium oxide. Okay, so for calcium oxide, calcium carbonate rather, okay, if we take the mass given to us in the question, so 8 grams, if we divide that mass by the MR, which is 100, so 100 grams per mole, then the grams will cancel, and we're dividing by moles, so we end up with an answer in moles. Okay, so let's so 8 over 100. Of course, we could do in our head, but let's be absolutely certain. So that's 0.08 moles of calcium carbonate, and from the equation, okay, from here, for every mole of calcium carbonate we decompose, we get the same number of moles of calcium oxide. It's a 1-to-1 reaction. So I'll just put that in there just to be clear. So that tells us that we're going to make 0.08 moles of calcium oxide. And to work out what that weighs, we just reverse this process. We multiply the 0.08 by 56. Okay, so for the calcium oxide, we're going to take the 0.08 moles that we've just worked out, multiply that by 56 grams per mole. Okay, and this time we've got moles and per mole, so they all cancel, and that'll give us an answer in grams, which is what we're after. Okay, so if we do that, so times 56, and that gives us 4.48 grams of calcium oxide, and the nearest person to that is our friend Charlie here, because he got 4.5. Okay, so if you round 4.48 up, obviously you get 4.5. So Charlie is our man, or maybe it's not a man. Okay, so that's the answer to that one. Let's move on. Okay, in stage 2, the slag that is formed contains calcium silicate. Calcium silicate is formed when calcium oxide, CaO, combines with silicon dioxide in a 1-to-1 ratio with no other product formed. Give the chemical formula of the calcium silicate formed in stage 2. So basically, we've just got to add these two chemical formula together, or the elements in them, we've got to add them together. So it's called calcium silicate. So let's start off with the Ca. As it's silicate, let's put the Si next. Okay, so there's 1 calcium and 1 silicon, and the other element present is oxygen, of which there are a total of 3 atoms. So the formula for calcium silicate is CaSiO3. Okay, iron reacts with oxygen to form iron 3 oxide. Complete the balance equation for this reaction. Okay, so we've got a couple of balancing boxes, but initially, more significantly, we've got a formula to discover. So just to double check, we can look at our table at the back, and we can find iron 3, which is Fe3+. So Fe3+, and we can find our oxide. Oxide is O2-. And to work out the formula, we need to work out how many of these we need to balance how many of those. So at the moment, they're not balancing. We can't add half charges in. We have to, all we can do is add whole ions in. So let's try adding an ion in. And that gives us a charge of 6+. This is 2-. So in order to make that balance, we can add in another 2 of these. Okay, and that will make this a 3+, and this a 6+, and this a 6-. So consequently, the formula for this compound is Fe2O3. Okay, so return back to our question. We can put our Fe2O3 in as our formula, and then to balance it, we can see we've got 2 ions here. So maybe we could put a 2 there. Okay, but we've also got a box there which tells us there's something else going on. So we'll perhaps take the oxygens, because the oxygens are completely balanced. So there's 6 oxygens here. So we will need 6 oxygens on this side. So to get 6 oxygens out of Fe2O3, we'll need 2 of them. Okay, so that makes the oxygens balance. And so now we can see that we actually need 4 ions, sorry, 4 ions, not ions, 4 ions on that side. Okay, moving along. So this is our acids and alkalis reaction scheme diagram with a bit of an added twist at the end. So the diagram shows a sequence of reactions from nitric acid. So here's our nitric acid. So this is the start point. And if we go to the right, adding magnesium, we're told everything we need to know about what's made. So it's an acid and a metal, which makes a salt and hydrogen. Okay, so the salt is magnesium nitrate. Going this way, we're adding a carbonate. So there's a little bit of mystery here. We have to work out solution A and gas B. So if it's a carbonate, we know we're going to get a salt, water, and carbon dioxide. So that identifies gas B. And the salt produced is going to be the product of copper with nitric acid. And copper and nitric acid would make copper nitrate. Okay. But then there's a little added twist here. You've got copper nitrate. If you add zinc to it, you get a further reaction and you get solution C and metal D. Okay, so this isn't strictly from the acids and alkalis syllabus. This is more from the metal syllabus, because this here is the displacement reaction, because zinc is more reactive than copper. So the zinc will displace the copper from the copper nitrate to make zinc nitrate and copper. Okay, so the metal D will be copper. So we use information in the diagram to name the following substances. So solution A, so we've got the nitric acid reacting with the copper carbonate. That's going to make our copper nitrate. Okay, so solution A is copper nitrate, which is what policemen get paid to work in the dark. Gas B, so this is a carbonate. So that tells us that gas B must be carbon dioxide. And then solution C, okay, so that's the result of a displacement reaction between copper nitrate and zinc. So solution C is going to be the zinc nitrate, because zinc is more reactive than copper and therefore will displace it from copper nitrate. So solution C is zinc nitrate. And metal D is the copper that's been displaced. Okay, right, a balanced simple equation for the reaction between magnesium and nitric acid. Okay, so that's this one up here. So we're going with Mg for magnesium. Nitric acid. Now nitric acid, you're given the formula in the question, which is handy. It's HNO3. And that's going to make magnesium nitrate. Now it's wise to check the formula of magnesium nitrate. So let's have a quick look at the back. So magnesium is Mg2+. And nitrate is, where are we, nitrate? Where are you? There we are, NO3 minus. Okay, so to electrically balance these two sides of the equation, we'll need 2 nitrates, okay, because each one is only got a single negative charge. So we'll need 2 of those. So this is an example of a formula that you'll need brackets for to encase the compound ion. Okay, so Mg brackets NO3 close brackets twice is the formula for magnesium nitrate. So let's put that in there. So Mg NO3 twice, and as this is a metal acid reaction, we're also going to get some hydrogen. Okay, so we could draw the block method, and that would be a very sensible thing to do. So let's do that underneath. So the Mg reacts with HNO3. That's HNOOO to make magnesium nitrate, okay, which is Mg, N, N, and 6 O's. 1, 2, 3, 4, 5, 6, because there's 3 times 2. So let's just make those into individual atoms. And the 2 H's for H2. Okay, so we've got one magnesium here. This is the dividing line down there. Let's make that clear. So one magnesium there, one magnesium there. We've got only one hydrogen here, and we've got two over there. So I reckon if we stick in an extra HNO3, that will make that better. We might find it solves all our problems. So we've got two hydrogens, two hydrogens. We've got two nitrogens now, which is handy because there's two nitrogens here. Six oxygens, six oxygens. So this is the balanced equation. So to make that true up here, we need a 2 there. Okay. Name the type of reaction that takes place between solution A and zinc. Well, that would be a displacement reaction. Because the zinc is more reactive than the copper and displaces it from the copper nitrate. Right, moving along. Now, the sulfate ions in sulfuric acid are identified using barium chloride solution. The equation for the reaction is shown below. So we'll notice in this equation, slightly unusually, they've given us the state symbols, which will help us to answer this question. So there's sulfuric acid, which is an aqueous solution. There's barium chloride, which is an aqueous solution. So these are both clear and colorless liquids. Then we've got barium sulfate, which is a solid. Okay, and we've got hydrochloric acid, which is an aqueous solution. Now the significance of this is that this is a white precipitate. So it is barium sulfate is insoluble in water, so it precipitates out and it makes the solution go cloudy. Okay, so tick the correct ionic equation for the formation of the precipitate. So it is that solid that we need to bear in mind, and because that's the precipitate. So we need to find a solution, the one that's got a precipitate. So it's not going to be that one. It's not going to be that one. Okay, so it could be this one. And in fact, looking at it, we've got the barium ion, which is 2+, and the sulfate ion, which is 2-. And if we weren't sure about that, we can just double check that in the back. So barium is here, and sulfate is down here. Okay, so it's a 2+ and a 2-. So without further ado, this is the correct one, because the other contenders, there's no need to overcomplicate matters with these multiple ions, and those charges are the wrong way around. Okay. So part 2, a student was asked to identify the ions present in barium chloride solution. Other than adding sulfate ions, state how the student could test for the barium ions, give the expected observation for a positive test. So barium is a metal, and the standard way of testing for metals is a flame test. Okay, and for barium, the positive result is apple green. Okay, so that's a pure memory or knowledge question there. There's very little information elsewhere in the paper for you to work that out. You just have to know your flame test colours. Okay. State how the student would test for the chloride ions and give the expected observation for a positive test. So for chloride, there is another specific test which you do need to know, and that is silver nitrate. Okay, so silver nitrate. And to illustrate the answer, we could perhaps write the equation. So the silver nitrate, okay, will produce silver ions and nitrate ions. Now we're not interested in the nitrate ions for this, because those silver ions will react with the chloride ions. So we'll use the same format as up here. That's AQ, react with the chloride ions. So that makes another rather exciting white precipitate. Silver chloride is a white precipitate. But that's all background information. All they want you to put in here is you get a white precipitate. PPT is the abbreviation for precipitate. Okay, so you don't need this bit here. That was just to help your understanding. Right, this question now, the comprehension question. A lot of reading to do. Okay, hydrogels are macromolecules. So macro basically means big, meaning they contain a very large number of atoms. Okay, I'm just repeating the question, the statement rather. They are polymers. Okay, so polymers are a form of plastic. made from hydrophilic polymer. So hydro is to do with water, and philic means to love. Okay, so or to like. This means they're readily mixed with water. Crosslinks between the polymer chains enable hydrogels to form their three-dimensional shape. Okay, the crosslinks that join the individual polymer chains together are formed by small reactive molecules that contain one or more double bonds. The interesting feature of hydrogels is their ability to swell and shrink depending on their surroundings. When in contact with water, hydrogels are able to absorb water and swell to many times their original size and weight, whilst maintaining the same shape. Being able to absorb water like this has enabled hydrogels to be used in a wide range of applications. For many of these applications, it is important to understand how the properties of hydrogels change with temperature. So table 1 shows how the temperature affects the properties of hydrogel beads in water over time. So if we have a quick glance down the data, so the starting point at no hours sat in water, this is basically the size of the beads initially, okay, and here's the diameter of the beads initially, and as we go down the temperature column, okay, the time, as we increase time coming down here, all of them start to increase in mass, okay, they get bigger, they get heavier and heavier, until we get to 8 hours, and we notice that the 40-degree temperature no longer increases, so it gets to a maximum size. So at 8.1 grams, the hydrogels beads cannot absorb any more water. And a similar thing happens with the diameter. So this is the diameter of each beads. They get bigger and bigger until we get to 8 hours, and then the diameter does not increase anymore. Okay, going across the temperature, we can see that increase in temperature does speed up both of the processes, so they absorb more water to become heavier, and they therefore get bigger quicker. Okay, so let's have a look at the questions. Take the statement that it best describes the molecule that form the crosslinks within the hydrogels. So over here it says that the small reactive molecules that contain one or more double bonds, and a way of describing molecules with one or more double bonds is that they are unsaturated. And it's referring to the amount of hydrogen there. Okay, so if a molecule is saturated with hydrogen, there is no double bonds. If it's unsaturated, then there can be double bonds. Give the phrase in the passage that shows the change the hydrogel undergoes is a physical rather than chemical change. Okay, so a physical change is one that can be reversed easily, whereas a chemical change it can't be reversed very easily, so we need to look for evidence of a change that can be reversed easily. So if we have a look in the text, okay, then we might find something that suggests that. So we know that they swell. What are we doing? Okay, right. So the interesting feature of hydrogels is their ability to swell and shrink depending on their surroundings. Okay, so the phrase we're looking for is swell and shrink depending on surroundings. So that suggests a reversible change, which is the definition of a physical change. Okay. Right, calculate the percentage increase in mass of the hydrogel beads, okay, when placed in water at 20 degrees C for 6 hours, okay. So we need to find the 20 degrees Celsius, so it's the mass we're after, so it's the first table, 20 degrees at 6 hours. So that's a key value there, and that's also a key value. So you can't see what I'm talking about. That's the key value, and that's key value because that's the mass of the bead after 6 hours at 20 degrees Celsius. So if we to calculate the percentage increase, we need to do 4.389 grams divided by the original mass, and then times that by 100. So So 0.035 grams times 100. Okay, so we'll refer to our trusty calculator. And let's have a look at that then. So 4.389 divided by 0.035 times 100. So 12,540. Okay, so 12,540%. Okay, so it's a massive increase there in mass. All right. Write a conclusion for the effect of temperature on the diameter of hydrogen beads in water over time. Okay, so as we mentioned earlier, generally an increase in temp increases the diameter up to 8 hours when at 40 degrees Celsius no further increase happens. Full stop. At 10 and 20, diameters continue to increase. Okay, so I think we've covered all the bases on that. Okay, so we need to be clear that they do increase going across the temperature range and going down the time data until we get to 8 hours for the 40 degrees Celsius one. Okay, right, moving along. Okay, so the last question now. So this is from the metal section. This is the extraction of aluminium. So in the information here, we're told that aluminium is extracted from its ore by electrolysis. Okay, the diagram shows a cross-section of the cell used for extraction. So little things we could add is that molten aluminium oxide is also known as alumina. We are told down here that the formula for aluminium oxide is Al2O3, and we're told that the overall reaction is to make 4 aluminiums and 3 oxygen molecules. What we're not told is the ionic equations. So we could remind ourselves that floating around in this molten aluminium oxide, we've got some Al3 plus ions, and we've got O2 minus ions. Because when you melt alumina or aluminium oxide, the ionic lattice breaks down and it frees the electrons, which is why electrical current can flow through molten aluminium oxide. The positive ions are attracted to the negative cathode, and the negative ions are attracted to the positive anode. So the question is a QER question. So we're looking for good communication, but then sound scientific knowledge. So explain the movements of the Al3 plus and O2 minus ions inside the cell and how the reactions at each electrode demonstrate oxidation and reduction. Include electrode equations in your answers. Okay, so opening statements might include that Al3 plus ions are attracted to the negative cathode. Okay, where they are reduced. Okay, now we need to explain what that means. Okay, So they're reduced because Al3+ ions, when they arrive at the negative cathode, they are basically given 3 electrons. Okay, and being given 3 electrons, they become aluminium atoms. Okay, and the definition of reduction in terms of electrons is reduction is gain. Okay, so reduction is the gaining of electrons. And that's from the acronym oil rig. So it's a good idea to remember oil rig. Oxidation is loss, reduction is gain. And then conversely, or oppositely, the O2- ions are attracted to the positive anode, where they are oxidized. And to illustrate that, so oxidation is loss of electrons. So actually we need 2 oxide ions, because when they arrive at the positive anode, they give up their electrons, they lose their electrons, and the 2 oxide ions become an oxygen molecule. So we need 2 of them, and because there's 2 oxide ions and they both lose 2 electrons, we end up with 4 electrons. Okay. And so oxidation is the loss of electrons. Now, technically, we've answered the question. Okay. However, we might want to go a little bit further to explain that the oxygen molecule then burns the carbon anode away, and we might also want to suggest that overall we have four. This happens 4 times. Okay. Well, actually, no. Let's not overcomplicate matters. We have, in fact, answered the question there, haven't we? We've done everything we were asked to do there. So we'll call that an end to this video. Let's see, I was any quicker on this one than the previous 3.